So, for the last talk of today, we have Pierre Colmez telling us about the Kirillov model for split cohomology.
Thank you. So, as the title says, I'm going to speak about completed cohomology, like in the previous talk, but maybe not in the same language. So L is going to be a finite extension of QP. And so the object I want to consider is the following one. It was defined by Emerton. So the projective limit over K of the inductive limit over N of the étale cohomology group of the modular curve of level N, geometric. So this is a curve over Q, and you base change to Q bar with value in OL mod P to the K. Okay, so that's one possible definition. The definition I prefer is in terms of group cohomology. So this is isomorphic as a group to the following group, H1 of GL2 of Q with values in the continuous function on GL2 of the adel of Q with value in OL. So if you write it in this way, you find that there is an action of Galois of Q bar over Q, the absolute Galois group over Q, which acts on this space because you start from something defined over Q and you base change to Q bar. And if you write it in this way, so here you have multiplication on the left. So this cohomology is, I mean, the action of GL2 of Q on this space is by multiplication on the left. And you still have the multiplication on the right. So you have an action of G of A, GL2 of A here. Okay, and so one nice way of writing it is this way, is that you are free to replace this space of continuous function by anything you want. So for example, you can replace it by the locally analytic functions. And then you are going to get the locally analytic vectors in H1 hat. So we saw in the previous talk another way to try to catch them. So I think this is easier, but and also Louis Pan told us that so this is related to p-adic modular forms. And Louis Pan told us that this is related to over-convergent p-adic modular forms, so over-convergent. So you could also replace LP by, locally analytic function by locally polynomial functions, and then this would be related to classical modular forms. Of weight bigger than 2. And so you can put your favorite functional analytic space here and get a new space. So that's two ways of viewing a completed cohomology. And the third one, which is going to be useful in this talk, is that you can go all the way to the top and say that this is also the cohomology of the modular curve, I mean, the entire tower of modular curves completed with value in OL. Base change to CP now. So this is as a group. So here you don't see the action of Galois of Q bar over Q anymore, but you see the action of Galois of QP bar over QP if you want. There. So now what we want is, well, maybe made a mistake. X0 is just the power of curves, and then you complete.
Oh, fine. So the cusp.
Well, when you go to infinity, it gives you the same result whether you complete or not complete. I mean, whether you put the cusp or you don't put the cusp. Yes. So I'm also going to fix a row bar going from the Galois group of Q to GL2 of KL. And I will assume everywhere that it is absolutely irreducible. And so you can look at H1 hat row bar, which is going to be the biggest subspace where all the Jordan-Hölder components of the action of Galois are row bar. So localized at row bar. And so what you want is a description of this H1 of row bar in the following, which has the following shape. So it should be rho univ tensor over some algebra R univ, so R row bar, let's say, with P of the dual of rho univ. So what are these spaces? So rho univ is the universal deformation of rho bar. R rho bar is the ring of universal deformation, but it is also a Hecke algebra. So sometimes I will call it T. So R rho bar equals T. So whenever I write it in this way, I want to view it as a ring of universal deformation. Of rho bar. And if I write it T, means that I just want to think of it as a Hecke algebra. And this is a representation. So this is a representation of Galois of Q bar over Q. And this is a representation of GL2 of the adels, well, in fact, the finite adels, which is built explicitly. So built explicitly from what you get from by the local p-adic, I mean, by the local Laplace correspondences in families. So I don't want to give the formula. Basically, you take the tensor product of all these things, and you get a completely explicit representation here, depending only on rho univ. There. So that's what you want. Okay. And so we have a theorem which says that, so first part is due to Emerton, that we indeed have such a decomposition. So, okay. If you replace this really completed cohomology by something a little tamer, so you complete only at P, and outside P, you you put locally constant things. So you replace it by the inductive limit over n prime to p, projective limit over k of inductive limit over n of h1 n p to the small n OL mod p to the k. And then I have to put many parentheses. Okay, so this is okay. And if you have some small restriction and star, you assume that p is not 2. So p is at least 3. And the representation rho bar, when you restrict it to the Galois group of qp bar over qp, is not scalar. So it's not chi plus chi for some character chi. No, sorry, no, that's not what he wants. He doesn't want chi, and star, some extension. He doesn't want the semi-simplification to be on of this shape. And it's okay if you replace this. And also, you will not get an equality, but you will get an isomorphism. So, okay, with some isomorphism and unspecified isomorphism, some abstract isomorphism of modules over all the groups that appear, namely the Galois group, the GL2 of the Adels, and also the Eke algebra. Okay? And so what we prove we prove the same thing, except that now, instead of having some unspecified isomorphism, we actually pin down one. So, okay, with equal, under the same hypothesis. And if you remove this hypothesis, what we can prove is that it is okay after inverting P. So, and okay after time series over OL with L if we are in the star situation. Okay with equal. But after transferring after inverting.
You said the group should then act first line, but it should act smoothly according.
It does not act smoothly on the first thing, but it acts smoothly here, yes. But the definition when you replace this one by this one, what you get, instead of having continuous function, you have functions which are smooth outside P and continuous at the place P. So that's a difference. Okay, so how does our proof go? Well, what we do is we construct Kirillov models for both sides, and then we match the two Kirillov models. Okay, so what is a Kirillov model? So in fact, so we define a model that goes from the left side, rho univ, sorry, the right side. And this diamond here has nothing to do with diamonds. It just means dual. But it's an R dual. So it's not an OL dual, it's an R dual. Yeah, so this goes into the continuous functions on the idels, finite idels. with value in something that I have to explain. So ohm over OL of this R, no, sorry, ohm over ZP of this R rho bar with value in A tilde plus. So what is A tilde plus? So A tilde minus. A tilde minus is A tilde minus A tilde plus. So I hope you are enlightened. And A tilde is W of C flat, CP flat. And A tilde plus is W of O CP flat. So that's what is called A inf nowadays. Yeah, so, and before it was called W of R, in fact. So at some point, Fontaine introduced A inf notation. And then I was writing papers, and it was impossible to do anything with Fontaine's notation, so I changed everything. So I called it A tilde plus for some good reasons. But so Fontaine was very upset that I changed from W of R to A tilde plus. And then later on, I used this A inf notation. And he asked me, but what is this stupid notation? So I had to explain that it was his notation, but anyway. Okay, so it's a little bit strange to see it appear, and it is going to be even so, yeah. And so this model is P of A infinity equivariant. So what is P? This P here is the mirabolic, so it's a star 0, 1 inside G, which is going to be GL2. And what is the action of P? Well, it's the usual action when you want to have a Kirillov model. So you let A be 0, 1 phi of x to be, well, some exponential term, P tilde A, EA of Bx, phi of Ax. And what is this EA of Bx? So EA of some adel y is just the product of the e to the power 2 pi I yl over L not P. And at the place P, you have to use this Fontaine's epsilon. It's not very important, but okay. So that's some character of the adel. So in usual Kirillov model, this would just be, I mean, it would be the product over all P, but here the place P, and so this belongs to A tilde plus. Okay, and what is the action of Galois? Galois. So if I take sigma in gal QP, sigma acts on phi by the following formula, sigma of phi of chi cyclotomic of sigma minus 1x. Okay, so we construct a map like this. So what is rather surprising is this the occurrence of A tilde minus, because there is no mention of it at all on this side of the story. And same, we also define something on the cohomology to the same space, and which is also equivariant and I should say that it is also equivariant for the action of R rho bar. Yes, so R rho bar of this equivariant. So it's equivariant for all the action we have, except that it is not equivariant for the entire group, but only for its mirabolic subgroup. And so because on these two space here, you have an action actually of the Galois group of Q and the GL2, you can upgrade this to something which are equivariant for this big group, but going to the induced representation. So you induce from P of A infinity cross GQP to G of A infinity cross GQ of this module. And then you get maps which are now equivariant for the big groups that you are interested in. And this way, you don't lose any information. And so what do we prove? So what we prove is first that this K tilde out is an isometry on its image. And this is almost tautological because, I mean, so what is complicated is to define precisely this, but the way it is defined is basically through the Kirillov model. So, I mean, maybe rather through the Whittaker model. So that's almost tautological. Then you prove that K tilde H is also an isometry on its image if you are under the condition star, if star, and it's an iso after you invert P if on its image, and iso after tensor L, if not star. So this is really not tautological. So that's basically what I am going to explain to you today. So that's quite complicated. It requires a lot of arguments. And now, what are the two extra ingredients you need? You need to know that if you start from locally algebraic vectors, you get the same thing from both sides. So image of locally algebraic vectors of both sides are the same. And this requires to understand the p-adic comparison theorem for modular forms and to go through the proof and do the computation that comes from the proof. And it also requires to understand, so on this side, there is one part which is a p-adic local Lagrange. And so you have to understand the Kirillov model of p-adic local Lagrange. So you have to match quite a lot of things. But I'm not going to say much about it. I'm just going to concentrate on this part here. And finally, what you use is the fact that these locally algebraic vectors are dense on both sides. And you use density of locally algebraic vectors. There. So once you have these four ingredients, then you have the theorem. So now I want to explain how you construct the Kirillov model for completed cohomology. The tilde is this one. So you start from something which is equivalent for this subgroup, okay? But you have an action of the big group on the left side. So you can get something equivalent for the big group, but you have to take the induced representation. Okay, so how do you construct this Kirillov model? So inside Y0 completed, you have the multiplicative locus. But you just take one component, connected component, so connected component of the multiplicative locus. So the ring of function on this thing. So when you are down in level 1, you just have a unit ball. So open unit ball. And so you have something over this unit ball. So the ring of function, O plus, let's say, well, you start from Z, you add Q and all its roots, and then you add all roots of unity in Q bar. So you get Q bar cyclotomic. Okay, and then you complete, for the PQ topology. And now, when you base change this to CP, you get a space that looks like B cross Z hat star, where B now is some kind of perfectoid open ball. So B goes perfectoid open ball. So what we are going to do is, as usual, when you want to do a Kirillov model. So Kirillov models are very related to Q expansions of modular forms. And so what we are going to do is restrict a class to this neighborhood. And then we have to have a description of this, of the Poetal cohomology of this perfectoid open ball. So I'm going to lie over CP. What?
It looks like you're working over.
So Z naught, you take your cusp, you fix a cusp, and you take the multiplicative neighborhood of that cusp. Yeah. Okay, so how do you compute this? So Peter explained to us how to compute this kind of things. So what is the Poetal cohomology of this B with value in ZP? Well, what you are supposed to take, you're supposed to take O of B, let's say O of B, not O plus. And you're supposed to take the tilt, then you're supposed to take the Witt vector and mod out by phi minus 1. Okay, so this is a lie, but not so much of a lie, because this would be true if B was actually closed. So what you have to do is use this formula I mean, you write your ball as a union of closed ball, and you apply this for each of these closed ball. And then if you are careful enough, you will notice that you have R-limbs problems. So to get rid of the R-limbs problem, you replace CP by a spherically complete field and so on. But I'm going to claim that nothing of this is necessary, okay? And so now you can actually compute this, and it's not so complicated. What you get the completed direct sum over all I in Q plus inter ZP star of A tilde minus times Q tilde to the I. So what is Q tilde? So Q tilde is just some tilt of Q. So it's some element, in Teichmüller of the tilt of Q, Q1 over P, etc. And what else? Okay, so how do you get this kind of results? So the first thing you have to notice is that you have if you have something in A tilde plus, then it's going to be in the image of phi minus 1. So that's why already you have A tilde minus, which is going, yeah, maybe I should tell you what this looks like. Surprise. So this W of O of B looks like A tilde, and then you have to add the Q tilde, this Q tilde here to the power Q plus, and then you have to complete. Okay, so already you have, I mean, this ring is expressed in terms of this Q tilde. So as I said, if you have something with coefficients in A tilde plus, it's going to disappear because it's going to be in the image of phi minus 1. And then because you have phi minus 1, so you have to know that phi of Q tilde is Q tilde to the P. So if you have any I that appears, by modding, I mean, you can replace it either by Q tilde to the P. I mean, you can replace I by Pi or by I over P. And so you can get to this subset here. So I which are in ZP star, okay? Anyway, so now you have, yes? And so this would be true, as I said, if you had a closed ball, and here you just have an injection, but that will be enough for what we want. So for a closed ball, it will be actually an isomorphism, and for an open ball, it's an injection. And so what can you do now? Well, this allows you to define a map alpha, which goes from completed cohomology to A tilde minus. Well, first you go to H1 pro etal of this B, ZP, and then you go to A tilde minus, and this here just take the coefficient of the term of degree 1. Okay, take coefficient of Q tilde. So you get a well-defined map from this. And now the model, so how do you build a function with value in this? Well, but you just do the following. So you define KH of vector V on X applied to some element lambda to be alpha, this alpha of X0, 0, 1 applied to lambda V. So here X is in A infinity star. And this lambda here is in R rho bar. Okay, so in this way, I define you a function on A infinity star with value in the dual of R rho bar. Okay, so you get this well-defined map, and you see the L theta minus appear. So on this side, it's not so surprising that it appears because it's related to p-adic theory. It's more surprising on the other side because it's nowhere in the definition. If I have some time at the end, I will explain where this comes from. Okay, so now what we want to prove is that this k tilde h that we define from this kh here by symmetrizing is actually an isometry or is injective. So the first theorem is the following. The theorem k tilde h is an isometry on its image if we are in one of the two following situations. P is bigger than 3 and rho bar restricted to gal qp is not chi plus chi, or if p equal to and the same thing, or rho bar irreducible, restricted to gal qp irreducible. So that's the first theorem. So let me explain to you how this is proved. So if you want to prove such a statement, you just need to know that it is injective when you reduce modulo p. That's what it means to be isometry on its image. So we need to show the injective modulo p. Or, so for p equal 2, you don't want the restriction to be scalar, and you don't want it to be irreducible. I think this can be removed, but
reducible case is always a good case.
yes, but here you will see my argument, I hope, and then you will see that I'm just at the limit of. If I could go just epsilon, further, I could remove it. And I have an argument that almost does this, but I don't know how to make it work, but it doesn't matter. I mean, it's true that irreducible is always a good case, but p equal 2 is always a bad case. So there is a balance between the two. So anyway, so you want to show that it is injective modulo p. And so you take an element of, you take the kernel. So the kernel, by construction, it's stable by all these things. So it's stable. Well, sorry, yes. So I should say here, k tilde h restricted to this localization at rho bar. So the kernel is stable by, well, as I say, I will call R rho bar T from time to time. So now let's call it T because T and gal Q and GL2A. But because you are in H1 rho bar, it's actually annihilated. So every element is annihilated. So rho bar corresponds to some maximal ideal of the big Hecke algebra that acts. And it's actually annihilated by some power of this maximal annual. So it's, and is M infinity torsion, where M is now an ideal of the big Hecke algebra that acts, and not only the Hecke algebra corresponding to rho bar. Okay? So the Hecke algebra corresponding to rho bar is just the localization of the big Hecke algebra corresponding to M. So M is the maximal ideal of T now. So the kernel is stable by this. And so I can pick an irreducible component. So let me see. What do I want? Oh, yeah. And so okay, so take an irreducible component. Component of the GL2 of QP circle of the kernel. Then now, because it is irreducible, it's going to be killed by M. So it's killed by M because it is irreducible, otherwise there will be a filtration. So it's killed by M, and so it means that the Galois action is, so it means it is rho bar isotypic. So it implies it is rho bar isotypic. Maybe I call it M. Rho bar isotypic. Okay, and now because we are mod P, and we have a representation of GL2 of QP, there is a fixed vector by the Iwaori. So there exists some V, which is fixed. What? Sokol. It means the, well, it is not necessary. And in fact, I exaggerate because I want to see gal Q. I want it to be stable under gal Q. Just mean you take a irreducible irreducible representation of the kernel. But irreducible for GL2 QP, not for GL2 of A. So it exists because the representation, the completed cohomology is admissible. And so there are some irreducible representations. Okay, so there exists some V in M, which is fixed by this subgroup, 1 plus P ZP, P ZP, 1 plus P ZP. So it means that you can find a copy of rho bar at a level which is very, very small with respect to P. So there is a rho bar which lives already at a finite level in the étale cohomology of this curve X of NP with value in KL, the residue field of L. So N is prime to P, and at P, I put this level here. But this curve here, now it has a semi-stable model of the extension of QP, where I join the P root of unity. So it becomes semi-stable over QP of mu p. And here we are in a good situation because the ramification index of this representation of this extension is p minus 1. So we are just at the border where Galois representation and finite flat Groth scheme correspond. We only have a problem if we are multiplicative or étal, where you cannot detect it directly on the Galois representation. Okay, but anything intermediate is taken care by the Galois representation. So that's something that will be useful. So now we have to use the fact that we are in the kernel of kh. So what does it mean to be in the kernel of k tilde h? It means that the class that we have is actually 0 in the neighborhood of the cusp. Okay, in each neighborhood of the cusp. And so what you get is that this what you have that your rho bar that you have here is inside the kernel of the map D log. So why? Because so you have a map D log that goes from this cohomology to differential forms. And you know that the differential forms you have is 0 in the neighborhood of the cusp, infinitesimal neighborhood of the cusp, modulo p. But you have one cusp on each of the connected component of the irreducible component of this curve modulo p. So this implies that the D log is identically 0. Okay, and then so your rho bar, you can view it as living in the p torsion of the Jacobian of your modular curve. And being in the kernel of D log implies that this rho bar lives inside this filtration introduced by Farg. So, well, G of P. So it's the group scheme attached to the P torsion. But in the level, I mean, in slope 1 minus 1 over P. So slope 1 corresponds to multiplicative component, and slope 0 is the étal component. Okay. So this uses those Hort-Tate groups, some explicit computations on Hort-Tate groups. And so now you have two cases. So two cases. So if rho bar is ordinary, then this implies that rho bar is inside the multiplicative part, G mult, corresponding to the M torsion. And but this, but you have a theorem of Gauche tells you that actually on this space, the action of Galois is through a character. But Gauche implies that action of Galois of GQP is through a character. Which explain why you cannot have two distinct characters in your rho bar. The restriction, so if rho bar is ordinary, then it also already kills everything except chi plus chi. Okay. Because otherwise it will, the action will be through a character. And now if rho bar is irreducible, then actually it is self-dual over some unramified extension. And so the slope is 1/2. But 1/2 is strictly smaller than 1 minus 1 over p, except if p equal 2. So which explains why in the case where p equal 2, we have to, I mean, we cannot treat the case where it is irreducible. Okay, but I have to say that, I mean, we are just at the limit, and I don't know how to make the arguments converge, but it looks like it should converge also in that case. Okay, so that's one case where you actually have an isometry. And now I want to give you the other. So the other injectivity result that we have is the following. So assume that you have W inside this H1 poetal of x 0. Now I invert P, well, I'm not really forced. And you suppose that it is closed. And it is invariant, stable by all actions, by T, GL2A, and Galois. And you also assume that when you look at the P torsion, where P is some maximal ideal of T1 over P, so this T here is really the big Hecke algebra. And now I'm not localizing at rho bar anymore. So you assume that this is 0 in the following case. So if by any change the rho corresponding to P is not irreducible. So if you are in the case of Eisenstein series, for example, or if the Sen operator of rho P restricted to gal QP is scalar. Then the conclusion is that K tilde H restricted to W is injective. So that gives you a big subspace. So in particular, if you localize at rho bar, where rho bar already is irreducible, then the first condition is empty because it's already irreducible mod P, so it's not going to be reducible in characteristic 0. And the second condition, Luepan proved that it is always true except in codimension 2. So these P bars that appear here are just twists of representation attached to modular forms of weight 1. And so they're living in codimension 2. So once you have that, it's not so difficult to deduce the injectivity for everything. But you have to add this extra argument by Luepan. Okay, so the key to this proof, the key to the proof is to look at the invariant vector, look at 1 ZP, ZP0, 1 invariance. So this is very much inspired by Luepan and Shenhao. we did the same thing, but instead of taking the entire completed cohomology, they looked at locally analytic vectors. And then instead of taking this invariance, they took things which are killed by the Lie algebra of this group. Okay. Okay, so the theorem is the following. We have several theorems. I don't have so much time. So we have an exact sequence. 0, H1. So now it's a coherent cohomology of X mod, let's call it U. Mod U with value in O goes to H1 poetal of X at 0 over C with value in C, fixed by U, goes to O of the Iguza curve at infinity, mod U. And here there is a -1, goes to 0. And so I'm not going to say much about the proof, but the starting point is this isomorphism of Scholze that says that this proetal cohomology, when you extend the scalar to C, is actually coherent cohomology. So it's the H1, no, it's proetal of X at of 0, C, but with value in O plus. And because I put C here, it's 1 over P. Okay, you start from this, and then you do the computation, and you end up with this exact sequence. And so what I should say is that so elements here are actually p-adic modular forms. And if you fix a character kappa from ZP star, ZP 01, ZP star, and you look at the kappa eigenspace, then you actually find the p-adic modular forms of weight kappa. Okay. And so now what you can prove is that if you have an element of the kernel of this Kirillov model, then it's going to live here. And why? Because you can check that this Kirillov model actually what gives you the Q expansion here. And so you know that if a modular form, p-adic modular form has a Q expansion which vanishes, then it is 0. So the kernel of K, the kernel of K tilde H lives like in here. Okay. And then, so the next theorem is that if you fix such a character here, you still have an exact sequence by looking at the kappa eigenspace. So kappa eigenspace is still exact. So you have H1 H1 poet U kappa, I don't need the U. And now the point is that you can actually compute the Sen operator on these spaces. And the sign operator here is minus the weight of kappa 2. So this kappa is just kappa 1 of tensor kappa 2. So kappa 1 on this one and kappa 2 on this one. And so the sign operator acts by the multiplication by minus w of kappa 2 on this space. And here it acts by minus 1 minus w of kappa 1. Okay, so if the sign operator on your rho p is not scalar, then your rho p cannot live here. Okay, so because now the kernel is stable under Galois, it gives you the statement I have, don't know where. So yeah, over there. That is, if there is, I mean, if you have something on the kernel, the sign operator has to be scalar. That's what it says. So if you have nothing in the no sub-representation on which the sign operator is scalar, then it is injective on this subspace. Okay, that will be it. Thank you.
Do we have any questions?
So do you mean you also have a arithmetic sample without taking the factors?
It seems so.
Oh, like it's true for H0, but it's false for H0.
False for H0. No, but I took here kappa eigenspace.
Okay. But sense constant.
Yes. Yes, then it's constant here. Yeah, so I mean, you need, yes, you need to know, if you want to apply what I said, you need to know that if you have a sub-representation of GL2 of QP, which is irreducible, then you can find a kappa for which there is an eigenvector, which in fact requires a classification of representation of GL2 of QP, which is rather a pain in the neck. It would be good to have this statement without this classification.
Any other questions?